All right, so let's look at this example here. So here I've got uh, a box section, right? That's 50 inches across and 15 inches high. Um, the skin on the top and the bottom is 30 thousandths of an inch, and the sides have a thickness of 100 thousandths of an inch. And then we have stringers on the top spaced every 5 inches. And this is on the right, we have the detail of the hat stringers, okay? Okay, and this section below here, this is the cross section. So maybe I'll put some axes on here. So let's call this X, Y, and in this case, this would be the Y direction, and this would be the Z direction. And so I showed it just over the rib spacing is 40 inches, A is 40 inches, and we have a uniform lift load on that section of 1,000 pounds per inch. Okay. All right. So the first thing that we wanted, well, we could do it either way. I mean, we could calculate the actual compressive force in the stringer first, or figure out the um, critical one. So let's do the critical one first. So the first thing we're going to need to do is get, so let's first calculate P critical for the stringer, right? And so we're going to, that's going to be pi squared E I, and now this is I of the stringer over the rib spacing squared. That's the length of the stringer. We're going to consider it pinned to pinned. All right. So we need to get the I of this stringer. Okay. And we know how to do that. And, we've done these things several times. But I wanted to show another way that's useful. In Hypermesh, that allows you to compute these sorts of cross-sectional properties. So it's actually quite helpful. So I've started Hypermesh here, and what we're going to do is we are going to go into Hyper Beam View. So over here on the left, with all these other icons here, we can go into Hyper Beam View, and that, if I click it, did I click it? Starts this sub application that allows you to actually get this. This is a way of actually, if you have an unusual section, this will get you the properties to go into a P bar or a P beam card to support modeling in Nastran or OptiStruct. Okay, so the way this works is you can sketch different kind of cross sections and whatnot. So I'm going to right click. There's tutorials on this you can find online, and we are going to create a cross section. You can draw them using this shell and solid section, but I think we have a standard section here. So I'm going to just pick a standard section so you can see you actually get a hat section. All right. And here you go. Here it starts off with the dimensions of a hat section. Now for us, down here, we have the dimensional values. So dimension 1 is this height. And so for us, that is 2 inches. For the thickness, dimension 2, we have 60 thousandths of an inch. Dimension 3, is the I don't know what you would call it, the span of the hat, right? That is 2 inches. And then the fourth dimension is the foot dimension, which is an inch. Okay. And let's let's see if I can zoom in on here. And so now, we've got this section as we want it to. Let me just center it. Maybe I can center it. What's going on here? Why do I do this? That works. Okay. Now on the right-hand side, you can see all the cross-sectional properties. So it gives us the cross-sectional area here. I know it's a little small, but maybe you can zoom in on the video. It'll also give you the location of the centroid relative to the coordinate system here, but you can see basically it's 0. The y is a little bit off. That's because of the way the dimensions are kind of defined. But basically, it's right on the center here. Okay. The other one to note that in this case, note where the axes are labeled, right? So z is to the right and y is up. So that is again corresponding to the element axes for a C-bar or a C-beam element, okay? We haven't talked about it yet, but there's the shear center is up here, and we also have the moments of inertia around the local axis, as well as the moments of inertia around the reference axis, I believe. Where are those? Oh, no, around the principal values, okay? But we want the local ones. What we really want is this I, again, we have to be careful. So IY using this is in the Nastran like notation. So this is the I that resists bending in this Y, vertical Y plane. So that, the way we've been calling it, is actually IZZ. And that's the one that we want, okay? So you can see that's the larger one, the 0.539, okay? And the centroid distance here is right in the middle, okay? I think that's all. I need the area, really need the area, and that IY, which again is IZZ, right? So, like I said, that's useful. You can actually I think you could draw your entire cross section in there as well and not use the spreadsheet that I have. And I've never done that, but I'm sure that would work quite well. Okay, so here, the area of the stringer, because we will need that to do some other calculations, is 0.4728 inches squared. This right here is right in the center, so that's 1 inch down. And okay, so this for us is the x and the y axis. So IXX, that's the one that we want, but this is what's called IY in Hypermesh. What should you call it? The thing we used again is Hyperbeam study. All right, that is equal to 0.5391 inches to the fourth. And I think that's all we really need, honestly. Okay. So again, this is aluminum. So Young's modulus is 10.3 10 to the 6th psi. And so here we can get the critical buckling load for one stringer. Again, this is a bit idealized because we're assuming that the stringer just, acts by itself. Obviously, it's supported a bit by the plate, more than a bit, quite a bit by the plate. But this gives us a very conservative answer. So that's the value of E. Now, again, we're going to use the I of the stringer, right? So this is going to be this one. So it's going to be the 0.5391 inches to the fourth over the rib spacing, which is the length of that column, which is 40 inches squared. And this turns out to give us, calculated it somewhere. Where is it? Oh, there it is. 34 kips. Okay, so if the actual compressive force acting in a stringer is 34 kips, then we have a problem. Okay, well, we need to figure that out, right? And so, this is not given to you directly. You have to calculate it from the lift loads. All right. So remember, to get this, the actual force in the in the stringer, is going to be, again, that change in the bending moment over the spacing of that rib section times Q. Now, this is going to be Q of the stringer over the I of the entire cross section. Okay. So we're going to need to compute all those. All right. So let's start off with delta M. All right. So in this particular case, what we have here is the distributed load, right? So on this side, we have M, and this is going to be M plus delta M. And the delta M comes from that distributed load over the 40 inches, right? So this is basically going to be the 40,000 pounds acting through the center, 20 inches moment arm, okay, on the edge, one of the edges. And so that is that's the total lift force on that section, and its moment arm is half. It acts through the centroid, so it's half of the rib spacing, which is 20 inches, and that gives me 800 kip inches. Okay, 800,000 pounds per inch. I'm sorry, 800,000 pound inches. All right, so that's the change in moment, right? Now, the Q, so this, the Q for the stringer, all right? So what we're going to do here is I'm probably going to exaggerate the dimensions a little bit. So this is going to be our A bar, and the distance of the centroid of the stringer from the neutral axis of the aircraft. Okay, so if we look at it, neutral axis of the box, right? So the total height's 15, so it's 7.5 from the neutral axis up to the top of the skin, and this is 1 inch, right? This is 7.5 inches. So this distance here, the Y bar is 6.5 inches. All right. So Q for the stringer is going to equal A bar, which we got from the hyper study thing. So that's the AST. Well, I'll just put it in here, whatever. That's the 4.728. 0.4728 inches squared times the Y bar, which is 6.5 inches. And that gives me Q for that one stringer of 3.073 inches cubed. All right. Now, the last thing we need is the I for the entire section. All right. So this has to be with all the stringers, top and bottom, and all that sort of good stuff. Okay. So we need the I for the full cross section. So that is going to be, for the sides, right, it's going to be 2 times the base, which is the sides are 100 thou thick, and the height is 15 inches cubed over 12. So that's the I of the sides. the eye of the top and the bottom skin, we're just going to do the parallel axis shift. So that is going to be its area, 50 inches times its thickness, which is 0.03 inches, times its offset, which is 7.5 inches squared, right? That's for the top and the bottom skins, and there's two of them. And then finally for the stringers, well, we have, if you go back and look at the original drawing, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 stringers, top and bottom. So again, we're using just the parallel axis shift on that. So we have 18 stringers. Their area is the 0.4728 inches squared. And their parallel axis shift is the 6.5 inches, and we square that. So that's the eye of the entire thing. And this turns out to be 675 inches to the fourth. So just to get an idea, the stringers by themselves is 478.7 inches to the fourth. So as typically is the case, even though the area of the stringers is not that huge, they really do a lot in giving us the eye for the entire cross section. All right. Okay. So now we can get the actual load, the force in one stringer. Okay. So that's going to be 800,000 pound inches times 3.073 inches cubed over 675 inches to the fourth. And that gives us a value of 3,639. Okay, and so there you can see actually this gives us a factor of safety of a little less than 10 to the actual critical buckling load for that stringer. So we actually have a pretty good deal of margin on there, okay? So that's how you go about doing this. Again, just be careful. Again, this is why we have to not just look at letters, but understand what the equations mean. So we use the right I's and Q's relative to what they are, right? So because we're looking at the buckling of the actual stringer itself, so we use the I's of the stringer about its neutral axis. But when we're figuring out the force, it comes from the bending equations for the entire cross section. So we use I of the entire cross section, and then the Q is of the stringer relative to the cross section. Okay. All right. So I'll stop there, and then next we will talk about spar spacing and how that's related to the plate buckling. Okay.